Acids are actually a pretty interesting category of substances, but we're actually not going to really talk too much about how they behave. This is solely about what we can do to identify them and name them in a consistent pattern. So first of all, know that acids are covalently bonded compounds. So with that in mind, we know that we're looking for a lot of nonmetals, but more specifically, we can usually know that if it begins with an H, if some formula has an H in it, then it's got to be an acid. The only exception we probably really encounter is water. That does start as H2O in its formula, but that's not really an acid. So anything else starting with an H will be considered an acid. If we're talking about nomenclature, right, not seeing the actual name itself, there's actually two categories. There's going to be one for binary acids and one for oxyacids. So know that, again, we're not talking about how they behave, which is a whole other conversation, which we'll have later on in the year. For now, we're just focusing on the fact that there are two different categories for names. Binary acids, which we'll abbreviate with just BA. The word binary shows up again, and hopefully you remember this from kind of the other uses of binary. Binary always refers to two different elements, right? Two, not just anything, but specifically elements. And since it's an acid, that means one of them's got to be an H. One of those two elements has to be hydrogen. Generally speaking, if you look for some of these details, you're looking for an acid, right, starting with an H. The two elements are going to be an H and something else, and typically it's not going to be any kind of oxygen, right? If it was H and then oxygen, chances are it'd be water. But we're not looking at that. Instead, we're looking at these binary acids. So let's talk about how we go from a formula to a name. Basically, if you're given a formula, right, a bunch of symbols, we're looking for the first word becoming hydro, using that prefix, and then you have a root element with the ic ending. So the first element, the first word always is hydro, element, ic. And then the second word is always acid. So let's take a look at these two. HCl, right? Out of context, how would I identify this as a binary acid? Well, first of all, there's two different elements. And also you notice that it's going to be two different nonmetals. So some of you might at first be thinking, okay, that's going to be a binary covalent compound. But this time we actually know more specifically, because it does start with an H, specifically because it starts with an H, and there's only one other element, it's a binary acid. So with binary acid nomenclature, we're going to apply the hydro prefix. So the first word is hydro. We're going to apply the element that corresponds to the second one right here. That's the root element. That's chlorine. So this becomes hydro, chlor, and because we have an ic ending, that drops the chlorine, right, from the, or we drop the ene from the chlorine and make it ic. This becomes hydrochloric acid. Right. Always hydro, element, ic acid. And then the second part, HBr, second word anyway, second example, is hydro, right? Bromic acid. Again, putting this into context, if I give you no prompting, you should be able to identify this as a binary acid because it's H and then one other element. So we follow this pattern of hydrobromic acid. Going the other way, from the name to the formula, generally speaking, what are we looking for? First of all, if there's an acid in the name, right, I think that's pretty self-explanatory. It's going to be an acid, but remember, it has to have the hydro prefix. Right? So it goes both ways, going from a formula to a name, going from a name to a formula. The hydro prefix is applied here. The first symbol will be H. The second symbol will be whatever root element it's going to be. So in this name, right, hydrofluoric, we're looking at the examples. Out of context, right, what do I do to identify this as a binary acid? We have acid, first of all, so we know we're talking about that family of substances. But more importantly, you see right here, it's got the hydro prefix. Other acids might not. These do. So hydrofluoric acid means we're talking about a binary acid. So all I'm going to do is start with an H, because binary acids, as an acid, it starts with an H. And because it's binary, we have one other element that's involved. And guess what? It's going to be fluorine. So hydrofluoric acid, HF. That's all it takes. Hydrochloric acid, we did this one earlier, but again, we'll go through the whole process. It's an acid. It's binary because of the hydro. And chlor is that root element that's involved there. So I'm going to translate that into a formula by simply doing H and then Cl, hydrochloric acid. Now, that was binary acids. Let's talk about oxyacids. Now, oxyacids, these are also acids, but as you can tell by the name, the prefix oxy generally refers to the fact that there's going to be some oxygen involved. Now, broadly speaking, looking for an oxygen won't always work out, but let's go and use that kind of as a nice little framework to start. Any acid that begins with an H and has an oxygen typically will be an oxyacid. Again, the exception being water, right? We're not really counting that as an acid here. But also, another great way to think about it is using a polyatomic ion. So if you have a polyatomic ion, right, the ones that you should have some memory of, or at least have some familiarity with, and you have an H in front of it, right, that's going to be an oxyacid. Let's talk about how we go from the formula to the name. So let's say, again, you're given a formula, and you got to translate it into words. First of all, the first word gets modified where the polyatomic ion, whatever it's supposed to be, that polyatomic ion has an ending sort of conjugation, an ending change. If an ion ends in ate, the acid form switches it to an ic. If your polyatomic ion ends in ite, then we switch it to an us ending. So if you remember, all the polyatomic ions, at least most of them, definitely have some ate or ites to it. So all you're doing is basically changing it to the appropriate ending. And the second word just becomes acid. All right, so let's try this out. Example number 1, HClO3. All right. First of all, out of context, what do we use to identify it is that H, right, is the starting letter. That starting element then lets you know it's an acid. But also, you have ClO3 afterwards. So you can either look at this as saying, okay, there's some O's involved, so it's an oxyacid. Or you can see that this is actually the polyatomic ion chlorate. The second way to look at this, right, using this as a polyatomic ion with an H in front of it, it's a much more effective way because that's where the name comes from. So the polyatomic ion, again, like we said, is chlorate. So that ate then, because we know we're talking about an oxyacid, switches to an ic. Ate becomes ic. Chlor, ic, and then acid. The second one, H3PO4. Well, all right, so H3PO4 again starts with an H. It's an acid. It's got PO3. Actually, I've been saying PO4. It's H3PO3. PO3 again is another polyatomic ion. That's the polyatomic ion phosphite, right? So phosphate. Actually, this is one of the funky ones, but instead of becoming just phosphorus, it actually becomes phosphorus, and then acid. So chloric acid and phosphorus acid. Right? So looking at the polyatomic ion, changing it from ate to ic, or ate to ic, ate to us, and then you write the word acid. So over here on the right side, you're kind of wondering what these pictures are. Again, this is kind of like a little tick on the top, and then this down here is a little inflammation. So if a tick bites you, then you get some inflammation where the ending, where the root word is itis, I-T-I-S. So ate, ic, ite, us. A tick, itis. A tick bites you, you kind of get a little inflammation, itis. That's a nice little mnemonic device. Some of you will just know it either way. Ate, ic, itis, no problem. But what about going the other way? Right? So in this case, if I am given a name, obviously the word acid will be there. Right? So something acid. But the key here is that it will not have, does not have a hydro prefix. Right? It does not have a hydro prefix. So I think I circled the wrong thing here. That's probably not as effective. Let's do the whole thing. It does not have the hydro prefix, right? So if it's an acid with a hydro prefix, it's an oxyacid. How do we translate this? We basically reverse the suffix, right? So if we had a suffix of some acid that ends in ic, we have to switch it back to the ate to know what polyatomic ion it came from. And then this next part is a little tricky. We're basically balancing charges here. Now, when we talk about balancing charges, we're typically talking about ionic compounds, and this is obviously not a bunch of ionic compounds. But for acids, there's actually some amount of sort of ionic behavior that sort of shows up. So there's a little bit of blending that might happen. Of course, these are all nonmetals that we're working with, so that definitely knows they're covalent. But there's, again, some workaround that we have to take into account here, where we do have to make sure that our H's, which are typically H pluses, those have to be added appropriately to our formula. So let's try this out. Phosphorus acid. This may look familiar here. So phosphorus acid, first of all, it's an acid, right? We know that. But is it a binary acid or is it an oxyacid? Well, let's take a look at the first word. We are lacking the word hydro in front, right? So I'm circling this one. That's not really the intent. The intent is that there's nothing in front of this phosphorus, right? There's no hydrophosphorus. It's just phosphorus. So because of that, we know it's an oxyacid. Lacking the hydro means it's oxy. So what polyatomic ion do we have? Phosphorus, O-U-S, comes from the polyatomic ion ite. So in this case, we're talking about the polyatomic ion phosphite, which is PO3 with a -3 charge. Okay. Now we have to slap on enough H pluses so that this becomes sort of neutral. Right? H pluses, they're all individual +1. So to make this work out, our formula will end up being H3PO3. So phosphorus acid becomes H3PO3. Notice how there's a lot of steps involved here, right? You do have to identify it as an acid. You look that there's no prefix involved. There's no hydro prefix anyway. Not having a hydro prefix means it's oxyacid. So we identify the polyatomic ion, phosphite, which comes from the us ending being switched to an ite. So phosphite, we have a formula of PO3 with a -3 charge. Then you add the appropriate number of H's to make it H3PO3. Like I said, this takes a lot of steps, so be sure that you're very clear about how these apply to eventually get these formulas. Example number 2 here, perchloric acid, right? Once again, perchloric acid, it's an acid. It's an oxyacid specifically because there's no prefix, right? So that means we have to look for the polyatomic ion that's relevant. Perchloric acid, the ic ending suggests that it comes from perchlorate. Perchlorate has the formula of ClO4 with a -1 charge. How many H's need to be thrown on there to make that a balanced compound? Just one. So your formula for perchloric acid is HClO4. All right. Finally, there's some practice here. Go ahead and put these to action. So you have a couple of rules that you can work with, and that basically takes care of it. Now, finally, just as a last thought here, bases, since they often are mentioned in the same breath as acids, we also kind of want to mention it. Just know that bases aren't, first of all, a part of this covalent compound. I wanted to bring it up because I just wanted to compare. It's a specific class of ionic compounds, right? Specific ionic compounds. These are actually metals and some hydroxide that goes with it. So the nomenclature, again, is going to be identical as any other ionic compound. So whatever the case, just know that there's a specific kind of ionic compound that are called bases because they have a hydroxide polyatomic ion. So NaOH, right? This, again, if you're looking at this sort of independently of anything else, any other knowledge, that's a metal. Hydroxide is the polyatomic ion there. So you just name it sodium hydroxide, regardless of whether or not you know it's a base or just a regular old ionic compound. And the same goes for these other two, right? TaOH3, it's an ionic compound because Ta is a metal. Hydroxide, metal, hydroxide, it's a polyatomic ionic compound, or you can view it as a base. But again, how you name it, how you translate it from a formula into a name is no different. And then finally, barium hydroxide, same idea. Barium, metal, hydroxide, polyatomic ion. You know it's a base because it has hydroxide, but you could just as easily treat it like an ionic compound. All right, that'll do it.